Now we go to the next step. We want to select a material for a cylindrical rod that has a specific or a specified length L, as you can see here, and it carries a tensile force F without failure. And we want it to be of minimum mass. Of course, minimum mass is always like a good objective. Minimizing mass is a good objective because it results in reduction of the cost in manufacturing and later when the part is working. So L is specified here, and the objective is to minimize mass of the rod. Of course, we have three variable, which is area and type of material that we want to select it from the list that we have in the CS software. Here maximizing the performance is actually minimizing the mass while still the rod can carry the load F safely without failure. Next step is to find an equation or relation for the function or for the quantity that we want to maximize or minimize it, and that's of course here is mass. Mass is related to area, length, and density, as you can see here. And as we said, three variables are A and materials. This is our objective function. We want to minimize this function. At the same time, we want to make sure that this rod withstand the tensile load of F. So the stress in this cross section, in different cross section of the rod, should be smaller than the strength of the failure strength of the material. That's what we show as here. So F over A, which is the stress, should be smaller than the failure strength. If you combine this and remove parameter A from these two relations, we end up to this relation, the new relation that you can see, force divided by mass over length times density should be smaller than sigma F. If we flip this fraction, then we will have m over L rho F is bigger than 1 over sigma F, or finally m is bigger or equal than this relation here. F is force, length, density over sigma F or failure strength. Here the last bracket contains the material properties. Of course, the lightest rod that can carry force F safely is the one that is made of the material with the smallest value of rho over sigma F. In other words, minimizing density over failure strength results in minimizing the mass. So density over failure strength can be our material index, but because usually it's easier to talk about maximizing, then we introduce our material index as the inverse of this relation. So here material index is going to be failure strength divided by density, and our goal is to maximize it. Let's go to the chart again, to CS chart. On the y-axis we have failure strength, which from this menu we choose tensile strength, and in the x-axis we have density. We press OK. Now we have different types of material, and because our goal is to maximize strength by density, so what we do, and the order is 1, so we draw a line that has slope of 1, and we insert it anywhere in the strength, tensile strength versus density chart. Look, because we here stated that we want to maximize the index, so any material above this line is accepted, and the line shows those material whose sigma F over rho is equal to 1. Sorry, my mistake. They have the same value of material index, which is tensile strength over density, every material in this on this line. And you see, by going to the left, we remove more material from the selection and less material is left in the list. If you want to maximize sigma f over rho, of course the last two groups of material that are left are metals and composites. If we have further uh, limiting or limiting properties like what we had in the previous video, then we can of course have a smaller range of material to select from. Thank you.